This lecture is brought to you by Megger, a leading manufacturer of electrical test and measurement equipment. I've trusted Megger's equipment for years and have witnessed firsthand their commitment to education and supporting technical schools across the country. For a limited time, Megger is offering my viewers an exclusive discount on their next purchase on products sold through U.S. distributors. Simply visit us.megger.com/bigbadtech for all the details. Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel. Today's topic of discussion is the transformer open circuit and short circuit test. Our objective is to introduce both the transformer open circuit or no load test and the short circuit test. We'll learn how to conduct these tests and how to interpret their results. Recall in the non-ideal transformers lecture, available at the Big Bad Tech channel, we introduced progressively more complex depictions of real-world transformers accounting for copper and iron losses, as well as magnetizing or excitation current. As difficult as that lecture might have seemed, these models were only part of the picture, and much more complicated and accurate depictions of transformers exist that account for other nonlinearities, including, but not limited to, series inductive losses and capacitive coupling between the primary and secondary windings and between the windings themselves. You'll be glad to know that only in the most extreme of occasions does one need to go to this level of detail, and often simpler models will suffice. Two field expedient means of testing a given transformer and accounting for these non-ideal effects exists: the open circuit test and the short circuit test. The open circuit or no load test is defined to quantify the parallel impedance component of the transformer equivalent circuit, whereas the short circuit test is designed to quantify the series impedance component of the transformer equivalent circuit. Field expedient, by the way, means an action that can be quickly performed in the field without the need of special apparatus. Often these tests are performed to quickly ascertain the series and parallel impedance components of a transformer equivalent circuit without worrying about divvying them up into copper losses on the primary, copper losses on the secondary, eddy current losses, hysteresis losses, etc., etc., etc. When you get right down to it, all you need is a parallel impedance and a series impedance for the transformer equivalent circuit. Let's examine the open circuit or no load test first. This one's pretty easy. As the name implies, this test is performed with an open circuit or no load on the secondary winding, such that no current flows through the secondary winding. The open circuit test necessitates a voltmeter and an ammeter be placed on the primary, or a wattmeter if you're super fancy, and then the rated voltage is applied to the primary. A small excitation or magnetizing current will flow in the primary, where the magnitude of this current is reflective of an imagined parallel impedance accounting for both hysteresis and eddy currents inside the transformer equivalent circuit. You note when the secondary winding is open-circuited, the reflected impedance seen by the source would be infinite, and current would only travel through the parallel impedance inside the transformer equivalent circuit. Given voltage and current readings, one can easily determine the magnitude of this parallel impedance as well as the apparent real and reactive power consumed by it. Consider a 5-to-1 step-down transformer designed to operate at 60 Hz AC with the following specifications: 120 volt rated voltage and 1 amp rated current for a total rating of 120 volt amperes. Using the primary to secondary turns ratio, it can be demonstrated that the secondary would produce 24 volts out. This means the secondary is capable of carrying 5 amps of current for a power rating of 120 volt amps. When the rated voltage of 120 volts is applied to the primary and the secondary winding is open-circuited, let's say the ammeter on the primary experiences 200 milliamperes of current, and current appears to lag voltage by 70 degrees. Keep in mind, no current is flowing in the secondary, and no power is being transferred to any load. This is the vampire leakage current I spoke about in the non-ideal transformers lecture. Any power consumed by this unloaded transformer is going to waste. An application of AC Ohm's law demonstrates the parallel impedance inside the transformer equivalent circuit is 600 ohms at an angle of 70 degrees. Which portion of this parallel impedance accounts for hysteresis? Which accounts for eddy currents? We don't know. We don't care. All these factors and more are rolled up in one quantifiable property inside the transformer equivalent circuit. A subsequent application of the AC power formula demonstrates the parallel impedance inside the transformer equivalent circuit at the rated voltage experiences 24 volt amperes of apparent power, of which 8.2 watts is directed towards real power and 22.6 VARs is directed towards a reactive interchange. You will note that the 8.2 watts of real power consumed by the parallel impedance inside the transformer equivalent circuit again is not being directed towards useful output, would be considered lost to this system. In summary, to perform the open circuit or no load test on a transformer, one opens the secondary, applies the rated voltage to the primary, and measures current flowing in the primary. The impedance, apparent, real, and reactive power consumed by the parallel impedance inside the transformer equivalent circuit can then be calculated by an individual well-versed in AC Ohm's law and power calculations.